Okay, so we're going to look at trig identities, and we have this one here. And the whole goal is to essentially show that the left side equals the right. So our parameters were that we're only going to work on one side, right? And we can't really work on the other. So we've chosen this more complicated one. And we've written one of the double angle formulas here. And the reason we chose this one here is because it looks very similar to our left side. And in fact, if I was to multiply this left side by -1, okay, so if I distributed a -1 in, I get -1 plus 2 cos squared theta. And that's what this is here. This is kind of like positive 2 cos squared theta minus 1. So with that being said, okay, since we multiplied this by -1, think of that like we have we have to balance the equation. So if I have -1 times this here, it'd be the same idea as -1 times this. So one of our goals might be to get to negative cos 2 theta. Okay, so we'll work with our right side, and this kind of being what we're aiming to do. So since we have an aim, and we know that we want to work with cos squared theta, we can work on trying to make all of these pretty much some version of cos. So like you said, let's work inside the brackets. What can we exchange tan for?
Sine over cos.
Yeah, perfect. So let's put sine x over cos x, which means what would cotangent be?
Cos x over sine x.
Yeah, cos x over sine x. Good. Okay, so we've got a version of it now. And on their other part, we could technically, can we do anything with sine to make it cos? Do you know any?
There's no 2, so I don't think so.
Okay, so good. So we have sine x, cos x. Okay. Now these two here are essentially opposites. We can get a like denominator if we want to combine them into one thing. Okay. So in order to do that, we would multiply one side. We'd pretty much multiply the denominator by the other fraction. So in this case, we're going to multiply sine x by both the top and the bottom. Okay, and on this side, we'll multiply cos x on the top and the bottom. Okay, so let's come down here. We get sine x, cos x. Here we'll end up with sine, and what would sine x times sine x be?
Sine squared.
Yeah, we'll have our sine squared x, okay. Subtract cos x times cos x.
Cos squared x.
Cos squared x, very good. And all of this is divided by cos.
Sine x, cos x.
Yeah, sine x times cos x. Very good. Okay. Is there anything that we've now created that we might be able to simplify? Can you think of any of them? How about the top of this equation? Do we know anything that the top of this equation might be equal to? Do we know any rules, maybe even from last year?
But it's a minus, not a plus.
Oh, you're right. Sorry, it is a minus. I was thinking of being a plus. Okay, what can we go for? Okay, so I was thinking of this being a plus, but you're right, it's a negative. So we can't do anything with that. If you think of distributive property or your fraction rules, this would be essentially the idea of multiplying fractions. If I turn this into a fraction, it would be over 1, right? So I do the top by the top and the bottom by the bottom. If you're unsure, I can show you a rule that's similar to this. Think of this like we have 5 times 2 over 5, okay? 5 times 2 will give us 10. 10 divided 5 is 2. So instead of going through all those steps, if I just actually realize that these two cancel or create a 1, it leaves me at just my answer, okay? Because these two values are the same. So with that being said, our sine times cos x and our sine times cos x are the same. So these cancel out or create a 1. And that would just leave us with our sine squared x minus cos squared x. Okay. Sine squared x and cos squared x. How about sine squared x? Can we change it into some kind of form of cos using one of our formulas? And maybe that being more closer to what I was talking about before. Do you remember your Pythagorean identity?
Mm-hmm.
Okay, so we'll write it out here. If we have sine squared x plus cos squared x is equal to 1, okay? What if we want to isolate for just sine squared x? We can move cos to the other side. So sine squared x is equal to 1 subtract cos squared x. Okay, and what that means is we can now replace this sine squared x with this value here. So we now have 1 minus cos squared x minus, and I'll write this in black because we haven't changed it, cos squared x. Okay. This then is essentially 1 minus cos squared x minus cos squared x. Okay, so let's kind of look up here. 2 cos squared. If you were to think of these cos squared x's, and maybe this is a little confusing, they have coefficients in front of them, and both of the coefficients are essentially
that's how you get the 2.
yeah, those are the -1. If you're unsure, sometimes students or somebody would use a let statement. Okay, you could say let a equal cos squared x, and it'll make a little more sense maybe when I do this. We'd have 1 subtract, now cos squared x is now a, so minus a, then subtract a again. Well, I know I can go -a minus -a. I should have equal signs here. -a minus -a is going to be -2a, right? So I have 1 subtract 2a, okay? But we know that a wasn't really what we were working with. Technically, it represents something, so we can plug that value back in for a again. So now we get 1 minus 2 cos squared x, and that is exactly what this side was, 1 minus cos squared x. So I thought we might be able to go here, but it turns out we found exactly what the left side was equal to.